online. And the first speaker is Pietro Maddio.
Yeah. Thank you. Good morning, everyone. My name is Pietro Davide Maddio. I am a researcher at the University of Catania. And today I'm going to present you a work entitled The Frictional Contact Formulations for Planar Mechanisms that I developed together with my colleagues from the same university, Professor Alessandro Camarata and Professor Rosario Sinatra. So let's start with a brief introduction of the state of the art of contact formulations that are very close to our formulation. The main methods for imposing contact are, in this case, the penalty method. Here we approximate the non-penetration condition, and we will focus on this method because our is based on the penalty method, and it's it's very easy to implement, but it's sensitive to the penalty parameter because we know that lower values generate unphysical condition, while very high values produces numerical instability. Then we have a Lagrange multiplier method that is exactly imposes geometric conditions, and we introduce additional variables that could be very high equations. And the augmented Lagrangian method combines the advantages of the two methods. So since we based it on the penalty-based formulation, here there is the three main schemes used for this contact formulation. The node-to-node scheme. In this kind of scheme, we are limited to small deformation because we need to match the nodes of the two bodies. Instead, in the node-to-segment scheme, we handle non-matching matches. It's widely used in FEM software, and it calculates the distance between the node of one body with respect to the segment of the other one. And the segment-to-segment scheme, it's like a precursor to mortar methods, and it provides high accuracy compared to the previous methods. These are the main characteristics of our method. We provide a direct calculation of the overlapping area between the master and slave body perimeters. We provide an efficient contact detection through a geometric collision test, and the global contact force is proportional to the intersection area, and its direction is determined using a weighted distances. It works both for rigid and flexible bodies. Feasible applications, it's suited for our communities, the multi-body community. That is characterized for mechanisms that are small deformations and large displacement. Our formulation is the floating frame of reference formulation, and is suited also for real-time simulations and gaming. So let's start with describing the procedure. We start with the discretization of the two bodies, the master and slave. I want to highlight that here we leave these nomenclatures master and slave, but in our method we can switch the two bodies because our method is symmetric. And once we discretize the perimeters of the two bodies, we can identify three different conditions: no contact, so the two bodies are not in contact. We have no internal nodes. Insufficient penetration, because only one node, if only one node is inside the other body, we cannot compute and we cannot proceed with our method. And tangent contact, the third, when we have exactly one node into a segment of the other body, we cannot compute the global force because we are based on the overlapping area. So once we are in the right condition, so at least one node of each body is inside the other, we can compute the intersection nodes, the two or more intersection nodes that we can have. And here, once we identified the correct configuration, we can determine the overlapping area by using the slave nodes, the master nodes, and also +2 in this case, because we had also the two intersection nodes. in order to have a more accurate value of the overlapping area. Moreover, we find also the centroid of the overlapping area, and the global contact force will be proportional with a penalty coefficient times the intersection area, and the penalty coefficient is proportional to the equivalent elastic modulus of the two bodies. So the magnitude of the global contact force is quite easy to find. Instead, for the direction, we need to have a more accurate procedure. First of all, we can identify one node, for example, the slave node here, and we can identify the direction that is orthogonal to the segment connecting the two adjacent nodes here. Then we find the distance dsi, where we intersect the other body perimeter. So we intersect a master node P star mi. And then the force, the calculation of the force will be equal to a pressure, another pressure, times the tributary area, that is this equation, so is the average value of these two length segments times the normal. And the pressure will be equal to the scaling factor, alpha s, times its distance, powered of q. I will give you more details about q. So the determination of the force direction is this formula. This is only for the slave body. For the master body, it's the same. So the direction of the global contact force will be the average of the two direction coming from the two bodies. So that's why it's symmetric. So the global contact force here will be proportional to the Kp times the area times the direction, and in order to taking into account also the behavior of flexible bodies, we need to decompose the global contact forces into the nodal contact forces. And we have to assure two equations, the force equilibrium. So the sum of, for example, the blue ones of all the nodal contact forces must be equal to the amplitude, the magnitude of the global one. And the torque equilibrium must be 0 with respect to the centroid. Here we can have in a compact form this equation. So here the Bs is the vector that is composed of the global contact force and 0 moment. And this parameter alpha, in this case, is the only unknown that represents a scaling factor. And this guarantees that all the nodal forces are repulsive. So here just a little video representing the behavior of the nodal and global contact force if we change the shape of the overlapping area. So we verified the method against the Hirth-Wyss theory benchmark. So we replaced exactly the configuration of two cylinders in contact. In this case, we have two equivalent radius equal to 8 meters. And here the equation for the plane strain equivalent modulus. And here we have a contact half width. It represents exactly this distance with the parallel to x-axis. And we can evaluate the resulting pressure distribution exactly in this overlapping area, where Pmax is given by this formula if we put x equals 0 because it's symmetric with respect to the y-axis. In this case, by adopting penalty coefficient equal to the value imposed with respect to the example reported in the Hirth theory of the Johnson's book, we can compare the two maximum values that given by the formula of Hirth theory is approximately 6.61 Pascal, and by extracting the maximum value of our method, we have an error about 0.37%. So confirming the good method. We compared against the STS method with inside a circular body, and here there is a representation of the behavior. It's elastic without friction, so it represents exactly in the second plot. You see the slave body vertical displacement, both with our method and the STS method. And we captured also the behavior over the time of the global contact force, and it matches exactly the STS method. We have an excellent agreement between the two formulations. Also, looking at enlargement of the nodal contact forces. Here is just a comparison of the STS versus our method, and I can say that unlike the STS method, we can exactly find the overlapping area, and it's not dependent on the triangular mesh, because in order to consider the global contact force, we can only discretize the perimeters. We need to discretize the bodies if we want to take into account the flexible behavior. So then we also applied the formulation for the tangential contact force. In this case, we need to find the relative velocity of the centroid over the overlapping area. So we find the velocity with respect to bodies, and the difference is the relative velocity. And we compute the versor, the unit vector of the global contact force. It is orthogonal to the normal one. And the friction force is equal to a coefficient times the signature of the velocity of the relative velocity times the direction, times here a regularization function. Here we adopted a sigmoid function, times the magnitude of the global contact force. We use a regularized function in order to provide a smooth transition between the sticking and the sliding regimes. Also, in this case, for the tangential forces, we need to decompose the global contact force into the nodal forces. And here, unlike the normal case, we cannot adopt the right-hand equation equal to 0, because we have to take into account that here we have a moment that is equal to the distance of the centroid with respect, by considering, for example, the slave body, with respect to the centroid, times the tangential force. And on the left end, we have, again, here, the sum of all the moments of the here it's quite small, but at each node we have the tangential forces that are orthogonal with respect to the nodal normal forces. And this SI represents, in fact, the vector from the centroid of the slave body to the ith node. Also here we can have a compact form. And again, here we have the only unknown, that is alpha tangential, that represents a scaling factor. We replicated again the previous example of the journal bearing, and I don't know why it stopped at the left example, but in this I try to Okay, start again. Here in the left example, we see that we don't have rotation because we don't have friction force, unlike the right side where we are taking into account the frictional effect. In this movie, we are representing the two behaviors, and on the color bar, we have the rotation of the two bodies, and we see that the yellow line remains the same. It's the case of no friction because we don't have rotation, unlike the other one that reach about 60 on 70 degrees of rotation. Our community studies the mechanism, so we tested our contact formulation in an ordinary gearbox. So we have a green body that is the pinion and the crown wheel characterized by geometric properties to R1, R2 with the teeth that gives us the calculation, in this case, of the transmission ratio. This is 0.44, the pressure angle, the thickness of the two bodies, the mass density, and here the penalty coefficient that is proportional, as I mentioned at the beginning, to the equivalent elastic modulus. And we adopt here the friction coefficient equal to 0.03, that in the literature it's a good value for lubricated gears. Also, the loading condition we impose to the torques. Then the driving torque is a value equal to 0.30 Newton meters with a cosine ramp in the first 0.5 seconds. Also for the crown wheel, we have a higher value, 0.45 with a cosine ramp, and a damping in the joint of the two bodies. And we can see in this animation the behavior. And here we report the ideal transmission ratio, that is the ratio of the two teeth equal to 0.40 and so on. And by obtaining the numerical transmission ratio, extracting the two angular velocities, the omega, the angular velocity of the crown wheel and the pinion one, we obtain exactly the same values. And also we evaluated the efficiency of the gearbox, and by using this formula here, we see that we obtain a value of 0.99 that is approximately the value that we can is obtained by experimental data for lubricated spur gears. So to conclude, we formulated a penalty contact method by using directly the formulation with the intersection area. We evaluated also the nodal contact forces, and we employed both rigid and flexible bodies, and we verified the method against the Earth theory and the STS contact method. Future developments, we will think about to extend the 3D contact using volumetric intersection and surface normal averaging, and the next step is large deformation formulation using the absolute nodal coordinate formulation. Thanks for your attention.
Thanks a lot. We have time for a very short question. There's one from the audience. It's not the case. Maybe you can comment on how you compute the lever for your balance of angular momentum with respect to the bodies or to the center of?
Oh, no. In the case of tangential contact force, here we take into account the centroid of the two bodies. The two bodies, yeah. And yeah, here you can see it. Yeah.
So let's speak again.
Thank you. Oops, yeah. Thank you. Just remember to stay in the square if you want to be.
Okay.
Okay, the next speaker will be Qiang. Please go ahead.
Okay, good morning, everyone. Yes, my name is Qiang from Technical University of Berlin. I'm now working as the chair of system dynamics and friction physics led by Professor Valentin Popov. My topic today is partial slip in contact of an elastic quarter space. So the keywords here is these two, one is partial slip and one is quarter space. So firstly, so half space is a very, so we are working in the area of contact mechanics. So half space is very often used concept in contact mechanics, for example, in classic Hertz contact. So it has half space has only one top surface. So if you put the indenter on the surface of the half space, it doesn't matter where you put the indenter on. Because the surface is infinitely large in this plane direction. But in quarter space has two surfaces, one top surface and one set surface. If you put the indenter on the top surface of the quarter space, then of course the contact behavior will be different if you put the indenter closer to the edge or far from the edge. So this is the contact behavior we are interested in. So the objective of this study is clear. So we consider contact between a rigid indenter and an elastic quarter space. So we consider only elastic contact and focus on the influence of the indenter location on the contact behavior. And okay, firstly, we look at briefly the the boundary conditions in this contact. So indenter is located on the top surface of the quarter space by a distant L from the edge or from the set surface. And the set surface is x equals 0 plane. So this surface is free. Free means the x, this is the set surface is x equals 0 plane. So the x component of the stresses should be 0 at this set surface. This means this one normal stress, sigma xx, and two shear stresses, is tau xy and tau xz. These three stresses should be 0 at this set surface. Here I will show you another simpler case. Why I consider this simpler case? Because this case is this contact problem is much easier to solve. In this case, the set surface is constrained in the x direction. So you can imagine that the set surface is leaning against to a rigid frictionless wall, or it is frictionlessly stick to a rigid wall. So in this case, only partial boundary conditions are satisfied. So this means that the set surface can move a little bit in this plane direction, frictionlessly, but it cannot move in this horizontal direction. And the solution to this contact problem is similar to this contact problem. So in this presentation, I will show this contact problem. Okay, how to solve this contact problem? The idea comes from Henty in 1970. He published a very very simple paper, but his idea was very, very smart. He did not propose a fundamental equation like Bosniewski or others fundamental equation. He used a very smart idea. His idea is to use half-space solutions to solve quarter-space contact problems by satisfying the boundary conditions, by these boundary conditions. So the aim is to remove this. If we can, we have a half space, but if we can remove these three stresses on the x equals 0 plane, then we get the quarter space solution. So there are two steps. The first step is to remove these two shear stresses at this x0 equals 0 plane by applying two symmetric identical forces on a half space. This means if we give one normal one load on the top surface of the half space and a mirrored load on the top surface of the half space, then in the middle, in this middle plane, these two shear stresses are 0. So due to the symmetry. Or if you can also use the fundamental equations to calculate the shear stresses on this middle plane. So these two shear stresses are 0. But the normal stress exists still. So the second step is to remove this normal stress. So by overlapping two half spaces, this step is relatively complicated. So there are some researchers tried to find a solution to solve to remove this stress. So this is a little complicated. I will not explain here. So we come back to the contact problem of this this contact problem. So for this contact problem, only partial boundary conditions should be satisfied. So no shear stresses on the set surface, but there exists normal stress. So we need only the first step of Henty's idea. So we just apply two symmetrical identical load on the top surface of the half space. Then we look at only the half, then we get already the solution to this contact problem. So it is much easier. 2 years ago, I presented this idea, and now but I did not show you the results. So here I will show you briefly the solution of the normal contact. But in this presentation, I will focus on the tangential contact. So the indenter is located on top surface, and the distance between the indenter center and the set surface is L. So this is an example of simulation result. This is the top view of the contact area, and also the pressure distribution on the contact area. So we can see the contact shape. The shape of the contact area is not circular, and the Hirth-Wyss stress at the cross section of this part is not the classic Hertzen contact. If we move the indenter further from the set surface, then finally we get the half space solution. So this is the case. The indenter is a little far from the set surface. So this is the h, and this is the distance. So you can see the solution is already close to Hertzen theory, and also the Hirth-Wyss stress in material. But if we move we put the indenter closer to the set surface, to the h, then you can see this the shape is totally different. So this result show you just a give you an impression about the normal contact. So experiment, you can also do very simple experiment. You just take a steel ball and press it on here rubber, rubber. Then you can see the contact area. If the steel ball is close to the edge, no. This is depend on the indentation depth. If you put the indenter with a smaller force, then the shape is still of contact is circular. But if you press it with a larger force, then the contact area is comparable to the distance. So the shape of contact area is not circular anymore. So this is it is indentation depth dependent contact area. So now we come to tangential contact. So indenter is pressed into the quarter space, then it moves in the tangential direction. Of course, yes, as I said, I consider this contact problem. Of course, the contact behavior is dependent on the sliding direction, and here I consider only two sliding directions. One is sliding perpendicular to the edge, and the other one is parallel to the edge. Under the assumptions of these assumptions, firstly we consider elastically similar materials. So this means tangential contact is decoupled with the normal contact. So this is also considered by in the classic Cattaneo-Mindlin theory. And the friction coefficient is constant at the interface, and the maximal tangential displacement until the cross slip is much smaller than the size of the contact area. So I show you here, firstly, the classic solution in the case of half space. So this is the classic Cattaneo-Mindlin solution. I hope, yes. This is a shear stress in contact area, and this is a stick and slip area. And these two are dependence of tangential force on the tangential displacement, and this is the size of the stick area depending on the tangential displacement. So this is a classic Cattaneo-Mindlin solution. And here I would like to mention this this result is a maximal tangential displacement until the cross slip. So in the classic, in the half space case, this maximal tangential force is independent of the indenter geometry. It is you have a sphere or cone or some rough surface. This maximal tangential force is independent of the indenter geometry. It depends only on the friction coefficient, the material, and the indentation depth. I think this is also what Professor Molinari questioned in the last session. Okay, now we consider the quarter space case. The distance is 0.5 times the Hertzen contact radius, and now it moves in this direction, perpendicular to the edge. So it is too fast. So again, and you can see here, this is the edge of the set surface, and this is contact area, and you see the stick area shrinks into shrinks during the sliding. And this is dependence of tangential force on the tangential displacement. And yes, we can see this maximal tangential displacement is smaller. smaller than the half space case. And in this simulation, gives a constant indentation depth. So the normal force in this case is also smaller compared with the half space case. And if we put the indenter at the different locations of the on the top surface, then we get these different curves of dependence of the tangential force on the tangential displacement. And if you focus only on the maximal tangential displacement, we can see if the indenter is located far from the edge, then the maximal tangential displacement is close to the half space solution, and if it is located closer to the edge, then the maximal displacement is much smaller. Okay, now we see this case. So the indenter slides parallel to the edge of the set surface, and this is a shear stress distribution, and this is a shrinking of the stick area during sliding. And we compare these two cases. This indenter slides. Maybe once again. Perpendicular to the set surface and parallel to the set surface. Okay. So we can compare these two cases. These are curves. Red curves are case of sliding perpendicular to the edge, and this is the case sliding parallel to the edge. So if we focus also again on the maximal tangential displacement, we can see in this case parallel to the edge, the maximal tangential displacement is almost the same. So it does not depend on the location of the indenter. So the reason is that but in this case it is much smaller. The reason is tangential contact stiffness. It is larger when the indenter slides perpendicular to the edge due to the restriction of the wall. So my hypothesis is that if the set surface is free, then the tangential displacement, the maximal tangential displacement will be larger when the set surface is free. So finally, I would like to show you this dependence. This is the ratio of tangential and normal force on the ratio of the stick area and the contact area. So you can see so in the half space solution or quarter space solution, they are almost the same. So it does not depend on the sliding sliding direction, and it is for half space or quarter space, they have the same, almost the same dependence. So this is all my presentation, and thanks for your attention.
Have you tried to slide diagonally in order to see the model is divided into fixed parallel and parallel?
So you may slide with an angle, or
yes, not parallel to the direction, but parallel as well. I mean,
not yet. So so now I consider only these two directions, sliding directions. So with an angle, I have not studied this.
Mixed,
I don't know. I have to do that. Yeah.
So then thank the speaker again, and we
Thank you. How should I?
Okay, so the next speaker will be Qiangfeng Lu, and we'll talk on a point-wise complementarity model for frictional contact problems.
Hi, everyone. Yeah, this is Qiangfeng Lu, research associate from McGill University. Here, I'm presenting the joint work with Professor Joseph Kovacic on a point-wise complementary model for frictional contact problems. A brief roadmap for this talk. First, I'll introduce contact problem formulation, then analysis the representative models, including SOCCP, LCP polyhedral, LCP cuboid. After that, I'll introduce our proposed model, adaptive pyramid, together with solution, then finally the results for behavior and scalability test. We start from a single dynamic simulation step. The first row is equation for motion. The second row is constraint equation, where the lambda and W are constraint force and velocity. Rearranging this equation, we got this force velocity affine relations. For a system with multiple contact points, for each contact point, it's represented in a local contact coordinate system, where the associated force and velocity forming the contact state. The Coulomb friction law imposes 3 key properties on this contact state. The coupling, that tangential force always bounded by the normal force forming this friction cone. The nonlinearity, that in tangential plane, the bond is forming friction disk encircled in all directions, then phase transition between open and closed, staking and sliding. So when we see contact problem, it consists of 2 relations. One relation from this system dynamics, forming the system equation, represent all constraints, and another relation comes from contact law imposed on each contact point. So when we build a model, it means how we represent those 2 relations together within a mathematical framework. The complementary problem, CP, is a general mathematical framework that defines a variable x and its mapping f. It imposes 3 conditions. X lies in a cone, f lies in a dual cone, and they are orthogonal, forming this vector-wise complementarity. So SOCCP is a contact model fitted in the CP framework, where the lambda is the variable, while W is the mapping from this system equation. While the admissible site of lambda forming this cone, however, the W doesn't naturally lie in the dual cone. It's a half plane defined by the non-penetration condition. So in order to fit into the framework, an augmented velocity W height is constructed through this correction nonlinear term G. And after that, this W height lies in the dual cone. So the SOCCP model is built by this augmented system equation, where lambda and W height now forming this complementary pair. We further analyze how this model represents the properties of contact law. For coupling and nonlinear, it's naturally preserved by this cone shape. For phase transition, it's implicitly represented by the vector orthogonal. So we see in the open case, like lambda come to the original point, while W height is the internal vector forming this open case. Then for staking phase, it represents W height to the origin point, where lambda is the internal vector. Well, for sliding is most special. Both lambda and W is a vector, lies on the bound of the cone and dual cone. And the orthogonality requires that their position has to be exactly opposite to each other. Now we can see the SOCCP faithfully represent contact law. It has the implications that it needs through the augmented system through an additional nonlinear term. Also, it's an implicit phase representation, which bring the complex and challenge in the associated numerical solvers. Next, the LCP is a subclass framework of CP, where the cone is requested to be a nonlinear orthogonal, while the dual cone is itself. With this condition, the vector-wise complementary from CP now reduced to component-wise, that each scalar component pair is requested to be non-negative, while one of them has to be 0. So the polyhedral is a contact problem fitted in this LCP framework. It has two constructions. The first construction is the whole tangential plane is represented by this discretized tangential directions like here. And the second construction is it imposes a global friction residue called G, represented by the normal force and the summation of tangential components. With these two constructions, each contact point now associated with number m+2 scalar complementary pairs. For the normal direction, it's lambda nwn. For the global coupling, it's G with a velocity offset called beta, where this beta is further added back to each tangential direction on this negative sliding velocity to ensure the whole term is non-negative. Then we check the property, how the model fit into contact law. While the coupling is approximated, nonlinearity is discretized. The sliding and skating, the phase transition is represented through those two-level complementary pairs. So first level is global coupling. In the sliding case where beta is positive, then in some active directions, we have positive friction force, while at this moment, the velocity is fixed at minus beta. While in other inactive directions, we have 0 force. On the staking case, we have beta equal to 0. Then on active direction, we have positive friction force, while 0 velocity. While in the other directions, we have 0 velocity, but at this moment, the model imposes positive sliding velocity on those directions. So overall, this model introduced augmented system, has redundant tangential basis, and distorted friction behavior. The next model is cuboid. This model is another contact model fit into the LCP framework, but very different from the polyhedral. It also has two constructions. First, the tangential plane is discretized exactly in 4 directions aligned with the tangential plane axis. And second, it provides a fixed a priori bound. So in this case, each contact point is associated with 5 pairs of complementary condition. In the normal direction, the same. In the tangential direction, it's a fixed bound minus friction force. Then it's the negative of the sliding velocity, so ensure this whole term is non-negative. And notice this original, this model, not like the last page polyhedral. This model preserves the original system equation. Although it has 5 pairs, but every 2 tangential pair along the opposite directions is imposed on the same scalar equation. So the cuboid model has clear advantage. It preserves the original system, has explicit phase transition representation, and independent tangential basis. Also introduce certain implementations that request prescribed friction bonds, loss of coupling, and anisotropic sliding. Now, after all the analysis of representative models, here we present our model formulation, the adaptive pyramid. Here is its model. This model has very similar structure as cuboid, that it preserves original system equation while have 5 scalar pairs along 1 normal direction and 4 tangential direction. The only distinct difference is this model, instead of a fixed friction bond, it uses state-dependent bond. A geometric illustration is here. Suppose we have already solved the contact state. We have the normal force form the circle and tangential vector is here. Based on this information, the friction bond along the x plus direction can be drawn this way, as well as other 3 directions. Therefore, the whole model forms an adaptive pyramid on the admissible side that based on the current contact state always align with the ideal friction cone. From the framework perspective, this formulation directly uses the original pair lambda and W, which naturally not lies in the cone and the dual cone structure. Also, the admissible set is not predefined, but state dependent. Therefore, this formulation does not lie in the standard CP framework. But on the other hand, it's faithfully recovers the properties of contact law. Here is a comparison model table, summarize all the 4 models, and we can see this adaptive model. It reaches the structure simplicity of the LCP cuboid while recovers the physics accuracy as SOCCP. To solve the model, we propose this solution framework. It has 2 stages. The inner stage is solve a fixed LCP cuboid problem. Here we implement a standard PGS solver, and after that, a post-solver phase-consistent projection is added. Then the outer stage is adaptive bound update. So this stage is not like the iterative convergence method, such like a Newton type method, not like that. But instead, it checks the geometrical mismatch between a friction box and the friction disk, classify the contact state into 4 different cases, then apply direct correction. So for case 1, if a resolved contact state, the force vector lies in both the disk and the box, it represents a consistent staking, so no error. For case 2, if a force in the friction disk representation lies outside, which represents a sliding motion. However, it still falls into the box, generate over-constraint staking. In case 3, if a force vector lies within the box along one direction, but outside the box along the other direction, which means the contact point at this moment is staking along one direction while sliding along the other direction. Then we will have sliding velocity is locked in the direction of box edge, generate this velocity anisotropic sliding. Well, on case 4, it's when a point is sliding along both directions. Then the force within the box reaches the bound on both directions, which means the force will locked in the direction of the box corner, generates this force anisotropic sliding. So based on this case classification and correction, then we are able to solve the friction box internally, then recover it back to the friction cone externally. And later on, the behavior test showing that only 2 loops, like 1 and 2, were able to address all the case 3 and case 4 error. Now the behavior test, this is the cube pushing. We apply a general external force on the cube, pushing the box sliding on the ground. When we solve with classical cuboid model, we can see we have force coupling error, where the result normal force and use the box has clearly offset. Also, we have also the velocity, the motion is locked along the box edge direction, generate this velocity anisotropic behavior. Well, solved with the proposed adaptive model, all the coupling and anisotropic issue has been resolved. Next behavior test is we apply an initial velocity, so the box goes through and then automatically stopped by the ground friction. In the cuboid model, the force coupling error still exists. Also, the force is locked in the corner, generates this force anisotropic behavior, and then the whole motion is deflected unnaturally. Then in the new model, like everything is resolved. We add this additional behavior test while the box starts with the initial velocity while rotating and braking. It's so fast here. But we can see that along all directions, like the adaptive box is able to catch up the changing of contact state, support a smooth and accurate friction behavior. Then finally, it's the stability test. We integrated the proposed model and solution framework into the commercial software Vortex Studio. And it is integrated seamlessly in the engine pipeline using standard LCP Sauer interface and reach stable and efficient simulation for large scale up to 1,000 cubes free falling down. And for the most challenging simulation step, with a single laptop CPU environment, it uses up to 10 to 20 millisecond step, supporting simulation approaching 60 Hertz. Yeah, that's the result. Thank you.
Thank you very much. We have time for questions. I have a few questions.
Yes, please.
You compared your adaptive permit, I think was the name, with respect to this simple LCP.
Yes, yes.
So how, I think you skipped this or I didn't get it. How do you adapt the box?
I see.
Cases, so the cases goes
Yes.
wrong, but how do you,
Thank you. Yes. So the idea is make the box align with the disk, like give a resolved context state, give you a resolved force vector. Then when the force vector represent in the box and disk, we aim for them to generate a same motion behavior. So let's see here, if you have this force and velocity, if you are able to adopt this box internal the disk, while the direction is aligned along this way, then it doesn't matter you use box model or a disk model, it will generate the same simulation behavior. So that's how we do that. And in this case, we clearly see velocity is wrong, but force is accurate. So we rescale the box based on the force. And on this case, clearly the velocity is okay, but force is wrong. So we rescale the whole thing based on velocity.
Okay, so you meant the left box in the next iteration.
Yes, yes, thank you.
Okay. Further question. Do you know, did you capture, how many iterations do your auto iteration take?
2. Only 2, yeah, because it's not meant to iterative to converge like Newton method. We don't have like those like a loss function, not like that. We just iterate to to change the shape correction based on the cases. So like one we can discover all the points in this, and another round we can discover all the points in here. So 2 points we are able to recover the ideal contact behavior. Yeah. We can have as many as possible, but just 2 is good enough to reach the accurate results. Thank you.
No further questions. We have still time. 1 minute, but we can just prepare the next talk. So thank you.
Yeah. Thank you. Thank you.
Nope.
You can also put it on that one. That's fine. Or not. No. I will put it here. Yeah. Okay.
So if you stand on the way forward, then the camera is.
Okay.
Yes, the next speaker will be Rolf Stenberg, and I think he will talk about Nietzsche. So please.
Right. Thank you very much, and thank you for the organizing this conference. It has been a success so far, and certainly will continue. Okay, so that's the title. I'm not going to talk about more about that. So let's look at the okay. 2 years ago, I gave a talk on penalty and Nietzsche, and then I thought, okay, now I have to look a little bit into augmented Lagrange and is there a connection with Nietzsche and so on. So what did I do? I'm a old style guy, so I pick up the books and print out a lot of papers, and then of course the coffee is important here. So I think there are 3 authors of 3 books sitting here today. Then I have my Bible, or the generation, for my generation in mathematical finite elements, is the book by CRA from 1978, kind of industry standard. So that's you always, okay, you refer to it, but you don't always check if it's there. But anyway, so, but the thing is that there's so a hell of a lot of papers today. So you get a little bit frustrated. So if your paper isn't in one of these piles, I apologize. And of course, when reading these papers, I never got really the answers to the questions that came to my mind. That, of course, doesn't tell anything about the papers. It's just telling something about me. Sleepy or senile or something like that. And then I thought, okay, I will try to be modern and use artificial intelligence. But I will comment perhaps on that later. But the answers I gave were quite a lot of hand waving and not very precise. To the specific answers, give me a reference to this, they didn't succeed. Okay, so I really saw this as a problem. And then there is also, I'm from a mathematical background, so there is really a kind of a cultural differences. So here again the classic, and if you open the book, there is on this page 2, there is a quotation by Helmsauer. So a mathematician's nightmare is a sequence n sub epsilon tends to 0 as epsilon becomes infinite. And then when you open the contact literature, it's exactly like that epsilon goes to infinity. Of course, that's a triviality, but it causes a lot of troubles when a guy for me that since 43 years ago, epsilon had always been a small number. I think in courses, proofs, anything. Okay. So, and then also in a sense, the methodology that you find in CRL's books, the notation, it's really geared to the mathematical analysis. And one can say now, 50 years later, it has been very successful. It works. But if I mock engineers, I should mock mathematicians, because this business is about INFSUB conditions, LBB conditions, Brabowska-Bretzi conditions, and the tradition is to refer to the paper by Franco-Bretzi, and it's impossible to read. I have it on my desk, kind of a souvenir, and every now and then. I learned this from a paper by a civil engineer and a book by a civil engineer, Ivo Babushka, and in this business, go to that one. But very few have read that paper. Okay, so so now to the point. So to study this, where is this? What happened with? Okay. Oh, okay, great. Okay, so here, just to have as simple a notation as possible, you take the basic thing, you have the Poisson equation, you cut it, and you have to glue it together with your favorite method. So this is the equations. And then I gave a talk 2 years ago and looked at the penalty method. And the message was that the penalty method is not consistent. So if you take the variational form, plug in the exact solution, it's not satisfied. So you are bound to have some problems. In optimization and finite elements, you see a lot on that it's sensitive to the penalty parameter and it's ill-conditioned. In optimization, you have just one parameter. It's of course in ill condition, but now we have two parameters. We have the mesh, number of elements, and they in the penalty method they get connected. and the message is that the penalty is never good. So a small penalty, we are far from the exact solution, and with the big penalty, now I'm talking about the convergence speed of the finite element method. So if you had a computer with infinite precision, the result wouldn't even be good. And on top of that comes the ill conditioning. And then the remedy for that is the Nietzsche, which is just two small changes in your code, and the consistency problem is solved, and you have a method that works. And the reference for that talk I gave you find in don't be afraid, Rakende de Mechanica, that means structural mechanics. It's on the web, and the paper is on ArcSci, so you can check it up there. Okay, so augmented Lagrangian. So as you know, I should stay here. Okay, so as you know, I'm a fan of Nietzsche, but I'm also a fan of augmented Lagrangian. In my first paper published, I used the augmented Lagrangian. And then, so now when I looked at finite elements, my first impression is, okay, what are you doing? You take the in a mixed form, use a stable finite element method with a discontinuous Lagrange multiplier so that you can eliminate or condensate or put the penalty term in element by element by just, and then you use the augmented Lagrange kind of a Usawa iterate. And in that way you have separated the problems that first you have the finite element analysis, you don't see the epsilon there, and then you have linear algebra where you have so the problem is just, the only problem that can happen is the ill condition in the linear algebra. So that was my thought. But then when I started to look at the system papers, no, people are not doing, this is not what they are doing. I said, it can't be true. No, it's true. And yesterday we have a talk that they just did it in that way. So, okay, now I put a question mark because this is really one of the questions that aroused to me, that if, so is it true or not, but my feeling that a lot of people do that, they write the augmented Lagrangian without discretizing, and then discretize or write it in the form, saddle for 4 and iterate, and then use a mixed method for that. And it's not the same thing as what I presented before. Okay, and then, okay, suppose the continuous problem in the augmented Lagrangian form, and then discretized with a mixed method, hopefully stable, and then iterate. And and what I found out immediately that for this alternative, there is no, at least mathematical analysis, and you really need it. Okay, so here is the continuous form. So here you have the Lagrangian, you have the penalty term here, and then you have the jump condition weighted with a test function for the Lagrange multiplier, and then you do it in a variational form. So you have the energy here, then you have a Lagrange multiplier for the jump, and I put a plus minus because is it this traction or that traction that you choose as the unknown. So that's the plus or minus here, and then you have the jump condition weighted by a test function for the Lagrange multiplier space. And then this Lagrange multiplier, as I said, it's the traction coming from domain 1 or domain 2. You can choose that. Okay. And then you iterate. So So, okay, again the same, you had the same problem. Okay, so here is again, so you throw the term with the Lagrange multiplier on the right-hand side, then you use the previous Lagrange multiplier approximation here, solve for this one, and then you update the Lagrange multiplier. Okay, and then on the continuous level, it's not difficult to prove that this will converge to the what you had on the previous slide. Okay, and then you go to finite elements. You see that when the iteration, okay, so first of all you choose spaces for the displacements, and the large multiplier puts the same thing, and then the iteration converges. So the previous Lagrange multiplier is equal to the present. Then you have a saddle point problem, typical fitting into Bretz's framework or Babushka's framework. You have this bilinear form, and then you have this symmetric form, and there you have the 1 over epsilon of the penalty. Okay, so if you see that, you know exactly okay, sorry. And then the question is, how do you choose the spaces? Okay, for the field variable, you use piecewise linear, piecewise quadratic, and so on. But how do you use the Lagrange multiplier? And what I think a lot of people is that if you have the, say, air body 1 here, you have a mesh, you get a mesh on the boundary, and then you say, use the same type of basis functions. So linear interior, linear continuous on that one. So that's, wait a minute. Okay, and then one has to prove the stability. So the stability is this famous infsub condition, but now what happens here is that the energy norm that comes from the bilinear for A, you have this penalty term. So when epsilon is small, this one is big. And then when you prove the infsub condition, when epsilon is small, what you would like to get, what you would like to get is the H times the L2 norm. But when epsilon is small, you don't get full stability. So what happens here that when this epsilon is small, you get too much stability for the displacement, and for the Lagrange multiplier, you get less stability. So what? Wait a minute. Okay, so that's the right norm. So again, too strong stability for the deflection, and too weak for the Lagrange multiplier if epsilon is less than H. But once it's bigger than H, everything is fine. So so yesterday the Lagrange multiplier was 10 or 10 to the power minus 5. It was the same. The same thing here is that this is a consistent method. You plug in the exact solution, and you can choose the Lagrange multiplier, but it has to be less than the mesh parameter. Okay, and then about this choice of using trace meshes, you don't really find for a uniform mesh, it's for me a triviality to prove the stability, and that was done a long time ago by my PhD advisor. This is easy to read. Then in the book by Joly and Hill Renard, you also use it for a uniform mesh, but then for a non-uniform mesh, they refer to some, and this paper and the same, there's a recent paper by Gustafsson, Robert, the same thing, uniform mesh, fine, but for general meshes, not so easy. And then there are 2 papers by Juhani Pitkaranta that really did this for the right if you know the singularity, the right mesh refinement. But these are horrible to read. I was his first student, and I cannot grasp what's going on. So I can't recommend it to. I will meet him in a couple of weeks, and then I ask him to explain it to me. But anyway, it works, no problem. But for a pedantic mathematician, okay. Okay, but then as I said, when epsilon is too small, you get stability problems, and you can see the effect also on the error estimate, because you have here, you have an error estimate, you have in the so to say quasi-optimality, but you have here in the L2 norm on the so when epsilon gets too small, this one explodes. So you see it in the error estimates. Okay. And again, the conclusion is that epsilon should be equal to h. Okay. So that's the conclusion. Always consistent. When epsilon is greater than h, fine, and so on. Okay, I have to. Okay, no, okay, so we have, so you know, to check numerically something that you have proved to be correct is a little bit strange for a mathematician, because either it proves that your proof is wrong, okay, then it's useful, or then it can prove that the coder didn't understand what you're trying to do. Okay, but anyway, you see, okay, so a couple of connections to Nietzsche. Okay, so we have, if you look at the augmented Lagrangian, the first equation, again, you throw the lambda to the right-hand side and then you solve. And the first choice is, in the iteration, is lambda equal to 0. So then the first step is the penalty method. Fine, already pretty near. But then, of course, you can argue like this, that the better approximation you have to this lambda, the better it should be. So, okay, so it's here. So then the question is, the exact solution, you know what lambda is. So instead, where you have this lambda h n minus 1, why don't you plug in the unknown? So you get, here the lambda, now you put this, connect this to the unknown. Okay, fine. But now there is no iteration. There is no n minus 1 here. It's just one equation for the lambda n. And this is a unsymmetric master-slave Nietzsche. It's easy to prove the convergence. The drawback is that you have a symmetric problem originally, as I said, Hermitian operator in Hilbert space and so on. So it's like Christmas Eve, you have everything. So if someone proposes an unsymmetric method for a really symmetric problem, I get a little bit. Okay, so then the next step is symmetrizing. Okay, that's okay. In the symmetrizing, you have that u minus 1 is 0 on the boundary, so you plug it in here as a symmetrizing term. And that's it. That's Nietzsche. Okay. So minor changes in the augmented Lagrangian, no iteration, stable, well-conditioned. And what I really love with Nietzsche is that it's so simple to analyze. Perhaps not to fit it on one A4, but on 2 you get the whole analysis. And well-conditioned. So if you get curious and have your augmented Lagrangian call, just try it if it works. Try if it works, and if you have some questions, you can ask me. Okay, and there's this set of questions that I had on the augmented Lagrangian, but I would be very glad to discuss with people who are using augmented Lagrangian to the questions that arise in my mind. Thank you very much.
Thank you. I would allow for a very short question or comment, otherwise we move on. Is there an urgent question? Then we go on. Thank the speaker again, and then go to the last.
Thank you.
Okay, so this is our last talk given by Roger Sauer, and I'm happy to attend. Please go ahead.
Okay, thank you. I have to be careful that I don't get trapped here in the cable. Yeah, very well. So, yeah, welcome to the presentation. I would like to talk about coupling chemical, mechanical, and thermodynamical contact. And let's see how this works. Yeah, this is motivated by various things. Adhesive bonding could be technical, could also be natural. For instance, this example here is osseointegration when an implant bonds to the bone naturally by essentially a healing process that would slowly form a bond. And since this is a chemical reaction, we were interested in coupling not just the mechanical and thermal part, but also the chemical part. And of course, there has been a lot of work in coupling two of those fields, thermomechanical contact, for instance, also the chemical and the mechanical part has been studied a lot, but the three-field problem does not seem to have been examined so much. And so that motivated us to look at this problem. I should mention the collaborators that were involved, Kranti from Berkeley, Tang and Katharina, who were PhD students of mine. Okay, very well. So I will talk a bit about the formulation and the potential that we use to describe this, and then directly jump to the numerical examples. So if one looks basically at the basic contact problem, there will be a chemical field in green, a mechanical field in blue, and we will be having two thermal fields. And the corresponding kinematic variables would be the bonding state, that describes how much it has bonded, the velocity jump, and the temperature jump, and then additionally an interfacial temperature that is considered independent here. And the corresponding flux variables would be the chemical potential, contact potential, the contact traction, a heat influx into the two bodies, and a contact entropy that can be sort of understood to belong to the medium that is in between, that could store energy and therefore also has entropy. So one can derive the general balance laws for the individual bodies in a classical manner and obtain equilibrium and I mean mechanical, thermal, and constitutive equations. One can do it also for the two-body system, and we have looked at conservation of bonding sites. So bonding is happening at a site that is supposed to be conserved, and then one can derive a reaction equation from that, and from these other balance laws, one obtains further field equations, which I will show on the next slide. So the bonding reaction equation would be first order ODE, where this is the bonding reaction rate that can be chosen. We will see that in a moment. The mechanical contact equilibrium is essentially the equilibrium of the contact tractions, and that's purely mechanical, how it's coming out of this setting. The thermal contact equilibrium would be essentially the energy stored in the interface coming from mechanical and thermal parts. And the constitution can be derived from the entropy inequality, and one finds the following 6 equations. So there are equations for the traction, for the interfacial entropy and for this chemical contact potential that derive from the interfacial free energy. And then there's some inequalities that I will examine. So in here, the GE would be the two parts of the velocity jump. And then additionally, I'm introducing a mean flux, which would be the mean of these two influxes here. And the remaining part, which I call the transfer flux, that would be the amount of heat transferred from one body to the other. And that's advantageous because this part can be then further found to have the following form. It contains the dissipation from friction, the dissipation from the chemical reactions, and interfacial entropy changes. So this piece can then further be examined and associated with an enthalpy, and then found that in case there's no friction, the reaction are either exothermic, isothermic, or endothermic, depending on the sign of this influx. So the interface can either give up heat or can store heat. Okay, if I come back to these equations, so they have been looked at before. So the interfacial potential in the thermomechanical setting, when there's no chemical part involved, can, for instance, be taken in this form and has been done by many authors, among them Todd's work. And that's a quadratic part in the mechanical piece. So this is the elastic gap, and there would be a quadratic part in the thermal part. And we'll be looking at the extension in a moment. Now, from these equations up here, one can further find then consistent models for sliding, for heat transfer, and for the bonding, and Coulomb friction would be one up here. Classical heat transfer that has been, for instance, examined in the context that the heat transfer coefficient is pressure dependent or gap dependent, which has, for instance, been examined by your work, Pietro. And in a similar way, this equation would suggest as the simplest model a linear relation between this chemical reaction rate, bonding reaction rate, and the chemical potential. And this coefficient here could then, in a similar manner as up here, depend on pressure and temperature. And that's what we will be considering, this linear relationship. So I said I want to extend this contact potential on the following slide. And the way we have done it is to keep those quadratic parts for the mechanical and the thermal part, and add a quadratic part that describes bonding and another one that describes debonding. So depending on what is your bonding parameter, this would be minimal in the fully bonded state, and this would be minimum in the fully unbonded state. And the two pieces in here would be then the bond energy that describes bonding, and that would be like a debonding energy. And in general, they could depend still on the mechanical gap and on the temperature of the interface. And the simple way that this could look like is that this sort of forward part, this bonding reaction, could depend on the pressure, which would be the gap in sort of this penalty setting. That would be the negative gap. And in the debonding case could be the positive gap, and this is opening. So basically something in this way where you basically have bonding when you're going into the penetration, and debonding when you're going into separation. And this, I would say, is more or less the simplest form, because everything is quadratic. All these pieces are quadratic. Also, these pieces here are eventually quadratic. So that would be the simplest way of constructing such a potential. And then one can derive the attractions, the entropy, and this chemical potential. And of course, one will get lengthy expressions because of all these dependencies, but then it's still, as mentioned, the simplest setting, I would say. And one can also study this analytically. So this is shown on this slide, which is looking at bonding of sort of two simple specimens under uniform temperature, also uniform sort of interface conditions. And if one considers a bonding potential like we had before, so the piece we had before where this forward energy is sort of, this bond energy has these two pieces. One is quadratically temperature dependent, one can calculate analytically that depending on these two pieces, one will either have a temperature increase during bonding or a temperature decrease. And this can be used later on to verify numerical results, which I will be showing in the following. One more thing beforehand is, so what are all the field equations and how are they sort of connected? So in classical mechanical contact, I would have two equilibrium equations that are mechanically coupled. In thermal contact, I would have two heat equations that are coupled. Now, additionally, they could be, of course, coupled in this way because of thermoelasticity. So these are four equations. Then there is the bonding equation for the field phi, which can depend on the mechanics by pressure, for instance, can also be connected to the last equation, which is the interfacial heat equation that is present and that is connected through heat fluxes with those equations and with this one, for instance, because of the chemical reactions that produce heat. And also there's coupling in this way because the pressure could, or the friction could affect the interfacial heat development. Okay, so that's basically the system. And now I have to admit, I have not studied the full problem yet with all those 6 equations. I have looked at a simpler case where this the heat equation is combined into a single one. And that is what I can show now in the next examples. The first one is still a simpler one. It goes back to this osseointegration example. And in this case, one can argue that the system is so stiff that it's really only a one-way coupled problem. The mechanical contact state drives the bonding, and there's no backward dependency. And the way we have looked at this is to simply investigate a contact-depending bonding law where the bonding would be optimal in a certain pressure gap range, and then beyond that range it would decrease and eventually it would not bond anymore, which is, I mean, physical, because if there's too much pressure, it's known that this bond will not form. The bone would rather be damaged. Likewise, if there's too much opening, also the bond is not forming. And the bonding now is a simple linear ODE that one can solve analytically given the mechanical state. So what we have looked at is played around with the mechanical state by choosing sort of some roughness, some asperities. And if you bring those into contact, you would get sort of a varying contact pressure state and a varying gap state, where in some places the gap is big and there would be no bonding forming, whereas in other places the pressure is large and one wouldn't expect a bond forming. And one can then say the evolution in a very simple forward, I mean, it's analytical because, I mean, at every point I just have this simple ODE. Okay, so that's the first example I have. Now let me look at a more involved example where there are now 3 fields first. And it's a rigid sphere I'm looking at in contact with a deformable membrane that is deforming mechanically. There will be bonding occurring. The bonding produces heat, which affects, through thermal expansion, the mechanics of the problem. And then in a second example, let me also make this now. There's also a set of parameters. So then, of course, there's another equilibrium equation. The results. So what I'm showing, contact pressure, so mechanical field. Down here, the bonding over time. So because of the contact, the bond will form. Below, the evolution of temperature. So as a result of the energy released in bonding, the temperature increases. And the boundary here, so the sheet is fixed. It's pre-stretched to make sure it's under tension. And it's pre-stretched always, I mean, fixed always on those 2 boundaries. And they're adiabatic, so there's no loss of heat on that boundary. So all the thermal energy will be sitting in the sheet. And one can actually now check that the analytical solution I've shown earlier is able to estimate correctly the temperature increase, and that is the case. So one can confirm that the energy is not lost. And then lastly, because of thermal expansion, because of the increase in temperature, the pressure will go down. Now the sphere is fixed, so since the sheet expands in size, the contact pressure will decrease. Now, so we can look at this in the movie. So we have run it a few times because this is running in parallel. So here the bonding state, for instance, is forming, and one can see that also over here. So it's increasing and approaches the contact area. At some point they will agree. Let me go back and run this again. So you can look at the temperature evolving simultaneously over here. It has a peak at the beginning, and then it's sort of, because the energy, I mean, the thermal energy is starting, temperature increases starting in the middle, and then of course it's conducted into the sheet. And the last thing maybe to look at is the contact pressure that is coming down. So that is the case where the sphere is fixed. So it's not going anywhere. If we allow the sphere to move, so that's the second example, then we're expecting, because of thermal expansion, that it will simply drop down. It will come lower, and so we can see that. So in this case, the thermal expansion is quite large, and the temperature increase is also significant, so that I can run it again, so that the sheet is coming down significantly and as a consequence, contact area is increasing, pressure is going down a bit because in this case the contact force was kept constant. So the net force is the same. As a toy problem, I also looked at the sort of other way around. You can also make the ball come up if you examine the Gauss-Joule effect, which is making the, I mean, in this case, the stiffness is increasing with temperature. That's a known effect in rubber-like materials. And if the stiffness goes up, then the deformations will decrease and the ball will have to come up. And so this is also something you can see here. So as temperature develops, the stiffness is increasing, and therefore the sphere is moving upward. In this case, I have to admit the temperature increase has to be very large to see large motion. But that's also good because this is then, in some sense, verifying the implementation that it can handle large temperature changes and large deformations. Okay, very well. So let me conclude. So it's a fully coupled thermal, chemical, and mechanical contact formulation. It's mostly motivated by natural bonding and also sort of industrial bonding, for instance, adhesive bonding. And we have studied this first from a theoretical point, looking at the balance laws and the constitutive equations, and looked at the potential that would be suitable in this framework. And it's the final implementation I have not included here for time reasons, but that is available in a monolithic setting. So far for the 4-field problem, the 6-field problem I haven't done yet, but I think we will be doing that at some point also. Yeah. So the theory has been published. The numerics, I hope, will be coming out soon. So with that, I'm done. Thank you very much for your attention.
Thank you. Time for questions.
Thank you very much for the nice talk. I have a curiosity. You say you are forming the bonding. So what would it happen if you start then unloading the sphere? Like, I mean, would you have like additions on the interface?
So I mean, the bond is forming a connection that now depends if you want to include debonding. So there are these two pieces. So you can basically have both. You can basically, I mean, in a general setting, you would have both of them active. And so when there is pressure locally at some region, the bond would be increasing. If there is tension elsewhere, it would be breaking. So it's, I mean, the bond breaking part is similar to many other models. I mean, you would be pulling, and at some point, you would. I mean, it's not purely mechanical. I mean, what would happen is that you, when you pull, is that there's a chemical reaction, or there's this diffusion equation, I mean, this first order ODE, which would decrease the bond, and then the things separate. So I have an example that I didn't show, but actually the example that I do have here also has a bit of debonding, because in this example, where the sphere is coming up, some contact is lost and some bonds are also lost. So there's also debonding in the outer part in this case. Classical cohesive zone models are purely mechanical. You have a damage parameter that depends on distance. So if you exceed a certain distance, the thing is damaged. But here the damage parameter depends on an evolution law. It's more similar to the Rouse model of adhesion. It's a pity he's not here, but I mean, this part is sort of a special case, I would argue.
Thank you very much.
And you said, because you assume that in your interface arrives at additional heat equation. So what kind of heat transfer do you assume in this interface?
So there are various ways one could look at this. I mean, you have three, in principle, you have three bodies, and you could have heat transfer between body one and the interface and the second body. Of course, you can then combine this, but you...
Can you assume, for instance, convection transfer in this interface law?
So this I have not included. I mean, the heat equation I have used is basically just sort of, there's transfer into the interface. But in principle, you could also have convection in the interface. But it's not included, this part. Also, there's no convection in the bonding equation. You know, the bonds are supposed to be sort of fixed. They're not diffusing on the interface, which is actually what you're getting in cells. When you want to study cell adhesion, the bonds, they diffuse on the interface, so you would also need a diffusive term in the bonding equation, which would make it more complicating also.
You were mentioning chemical reactions. Can the framework describe the creation of a new material, which is not body one or body two, as a product from a reaction? Or the interface is within
in this setting, the interface has no mass. So it has entropy, it has energy, but it doesn't have mass. I mean, you would, in principle, also add mass to the interface and then perhaps expand this framework. But at some point, you would be looking at three bodies, a three-body problem, which I didn't look at.
There will be an announcement, but first, thank the speaker again. Announcement is about our picture of all participants for this monthly conference. We are going to have lunch, and then he will meet at 10 minutes after 2 o'clock, which is 2:10, at the stairs at the main entrance of this very building. Okay, 2:10 stairs this building. Thank you and enjoy lunch.
The model is slower than the evolution of this.
I don't know. Just understand.